The grim reality that awaits us all is that we will experience the cycle of life and death. But this natural process is not exclusive to life on Earth. Even the stars and planets that fill our sky with light have an expiration date in our universe. A nebula, including our Sun, starts in a dense region and starts to compress and warm up. This is frequently the result of one of the various events that might lead to the gravitational collapse of a molecular cloud. Matter can be torn by galactic collisions or a powerful local supernova explosion, which would send it hurtling into the clouds at very high speeds. Each of these stellar labor rooms is capable of producing anywhere from a few dozen to thousands of stars. To create a star the size of our Sun, which measures 864,400 miles across, it would take a collection of gas and dust 100 times the size of our solar system. This is just the start. After such a massive accumulation of gas and dust has developed, it will eventually create a protostar. It is still recognized as a protostar as long as the material is still falling inward towards the object. For our Sun and stars of the same mass, the protostar phase would have ended after around many years. The protostar then stops expanding and radiation obliterates the protostar's material disk. A brown dwarf will emerge if the protostar was unable to amass enough mass. These poor little guys are substellar objects that are unable to maintain hydrogen fusion reactions in their cores due to a lack of mass. The fact that the main sequence stars don't have an issue with this makes brown dwarfs envious. A brown dwarf is, to simply put it, neither small enough to be a planet nor massive enough to be a star. Although this was merely a notion before 1995, it is currently believed that one brown dwarf exists for every 6 stars. If the star is large enough to fuse hydrogen atoms into helium, it will enter the main sequence phase, the same as the Sun. The main sequence period comprises the majority of a star's lifetime. Only nuclear fusion, which converts hydrogen into helium, prevents the star from collapsing at this time. Main sequence stars comprise approximately 9 out of 10 stars in the cosmos. A star's size determines how long it spends in the main sequence phase. These stars can be as massive as 200 times the Sun or as little as 1/10 of the Sun's mass. Despite having more fuel available, a star with a larger mass will burn up that fuel more quickly due to higher core temperatures brought on by stronger gravitational influences. A star that is the same size as our Sun will remain in this phase for years, while a star that is 10 times as massive as our Sun will only do so for a short time. The main sequence period will be followed by the star's transformation into a red giant. Red giants are dying stars that are in the terminal stages of stellar evolution. Eventually, our Sun will die and enlarge, swallowing up the inner planets and possibly even the Earth. After a star stops fusing hydrogen into helium, gravity will take over, and things will only get worse. Red giant stars can grow to a diameter of 62 million to 621 million miles, or 100 to 1,000 times the current Sun size. When one widens a raster graphic, the star's energy is dispersed over a bigger region similar to how pixels are spread out. As a result, the star cools down, losing only slightly more than half its heat. The red giant gets its name from the fact that as temperature changes, stars begin to shine more in the red portion of the spectrum. A star's size determines where it goes after this. Starting with less violent action, white dwarfs can form from smaller stars that have up to 8 times the mass of the Sun. These archaic relics of the stellar disk are very thick. One extremely powerful teaspoon of their material would weigh 5.5 tons, or as much as an elephant does on Earth. Although the radius of a white dwarf is only 0.01 times that of the Sun, its mass is similar. Astronomers can learn more about the age of the universe by estimating how long a white dwarf has been cooling. A white dwarf will eventually cool down to the point that it becomes a black dwarf, which emits light at the same temperature as the microwave background and is therefore undetectable after an unimaginably long period, tens or perhaps many years. There are no known black dwarfs due to the antiquity of the universe and what is known about the older stars. In contrast, a star with at least 8 solar masses will have a dwarf that is much more beautiful and much more violent. When a massive star runs out of fuel, a supernova can result. Supernova explosions send their interiors hurtling into space at velocities between 9,000 and 25,000 miles per second. We all carry the relics of these explosions in our bodies, since they produce a large portion of the stuff in the cosmos, including certain heavy metals like iron that contribute to the formation of both ourselves and our planet. New stars are born from the stardust left behind in the same manner as before, and the cycle repeats itself with a new generation of stars. That does not imply that the star's remaining components have reached their destination. A supernova explosion leaves the star's core behind, either in the shape of a black hole or a neutron star, both of which are ferociously beautiful and extremely destructive. Our highly enigmatic objects contain few neutron stars. They are so dense that if one were to take the mass of our Sun, double it and then condense it to the size of Los Angeles, it would approximately represent the density of a neutron star. A brand new neutron star would contain a cubic meter that weighs slightly under 400 billion tons. However, because of their density, their surface gravity is quite strong. On the other hand, what's left over after the supernova may develop into a black hole. Space is pulled away from black holes. To have the necessary gravity to draw in light, they must have an enormous mass and a little volume. To put this into perspective, imagine compressing the entire world to the size of a pea to create a black hole out of it. Nothing can escape the clutches of a black hole once it reaches its event horizon, since these enigmatic and terrifying objects have the power to slow time, rip you apart, and devour you. Everything it touches is permanently lost. There is the cosmic bully from the background. In contrast to bullies on the playground, we might have to rely on them to survive. Some scientists believe that black holes, which disintegrate stuff into subatomic particles, are involved in the production of the elements. These little specks are everywhere. The stars owe us our existence. You cannot disagree that stars are some of the most beautiful and lyrical objects in all of existence, no matter how big or small, how old or young. The bright red supergiant star Betelgeuse is believed to have effectively blown its top in 2019, losing a sizable amount of its visible surface and resulting in a massive surface mass ejection. After examining data from the Hubble Space Telescope and numerous other observatories, this conclusion was made. This is unheard of and is visible in a regular star's activity. The Sun regularly ejects chunks of the delicate corona, its outer atmosphere, in what is known as a coronal mass injection. The Betelgeuse SME released many times more mass than a typical CME. It is still trying to return to equilibrium due to the cataclysmic disturbance caused by the monster star. These discoveries provide insights into how red stars lose mass when their nuclear fusion furnaces burn down before bursting as gas supernovae. The degree of mass law has a big impact on what happens to them. The star's strangely irritable demeanor, however, does not indicate that it is poised to explode anytime soon. The mass loss event is, therefore, not always a warning of an impending explosion. To solve the riddle of the star's obstinate behavior before, during, and during the explosion, scientists are hard at work examining data from various sources. This also includes fresh spectroscopic and imaging data from the STELLA Robotic Observatory, the Solar Terrestrial Relations Observatory spacecraft, the Shell spectrograph, the Tillinghast reflector at the Fred L. Whipple Observatory, the American Association of Variable Star Observers, and the Hubble Space Telescope are all examples of space telescopes. A large surface-to-surface mass ejection of a star has never before been seen, according to experts. What we are seeing is something we cannot fully understand. It is comparable to following the real-time evolution of stars. The Titanic outburst in 2019 may have been caused by a convective plume that emerged from the star's innards and was more than 1 million miles wide. Due to shocks and pulsations caused by the cooling component of the photosphere, which blew off the piece, the star now has a substantial cold surface area beneath the dust cloud. Right now, Betelgeuse is having a hard time recovering from this injury. Broken pieces of the photosphere shot into space, where they cooled to form a dust cloud that obscured the star from our perspective on Earth. The dimming, which began late in 2019 and lasted for a few months, was visible even to amateur astronomers. Betelgeuse, one of the brightest stars in the sky, may be found on Orion's right shoulder. Astonishingly, the supergiant's normal pulsing rate of 400 days appears to have temporarily slowed. Observing variations in Betelgeuse's brightness and surface motions, astronomers have been measuring this rhythm for some time. The severity of the blowout is demonstrated by its disruption. The star's interior convection cells may be sloshing around like a washing machine tub that is out of balance. TRES and Hubble spectra indicate that the outer layers may be returning to normal. However, the surface is still bouncing as the photosphere rebuilds itself. Even though our Sun occasionally ejects tiny fragments of its outer atmospheres into space, astronomers have never seen a star's visible surface erupt into space to such a great extent. This suggests that the mechanisms responsible for coronal mass ejections and surface mass ejections may be distinct. To track the ejected debris as it travels away from the star in infrared light, astronomers may use the James Webb Space Telescope in the future. If Betelgeuse were to take the place of the Sun as the solar system star, its outer surface would reach past Jupiter's orbit. Do you think people will still be around after the Sun explodes?